So, hello everyone. Today we're going to talk about diodes and their characteristics. So, let's start. The term diode refers to a two electrodes or two terminal device. A semiconductor is simply a PN junction with connecting gate on it. Let us understand what's PN junction first. So, PN junction is nothing but a semiconductor which has two junctions, namely P junction and N type junction. So, these two junctions have a depletion region between them, and these would have holes, the p junctions, and the n junction would have electrons in them. So, and when the p junction and the n junctions are connected to a terminal, it's referred to as a diode or a p-n junction semiconductor. So this is how a diode is represented as, and this is the positive, and this is the n type, or this is the anode, and this is the cathode. I mean, this is the cathode, and this is the anode of a semiconductor diode. And we'll further see how a diode works. A PN junction provided with a copper wire connecting leads on each side, becoming an electronic device known as diode. So this is what we saw right now. When we connect a semiconductor, PN junction semiconductor of both sides with a connecting lead or a copper wire, it turns into a semiconductor diode. It can be used as a switch on when forward biased and reverse biased off when biased in reverse. So let us understand this. Let's say this is the diode. I'm sorry. So this is the diode. We know that this is the positive side and this is the negative side. When this is connected to a negative side of the terminal, and this is connected to the positive side, this is termed as the reverse bias. And when the same thing, when a diode is connected to a terminal or connected to a circuit where the positive side is connected to a positive terminal of a battery and the negative side is connected to a negative side of the battery. This is termed as a forward biased. So what happens is when a circuit is in reverse biased, wait, when a circuit is in reverse bias, it acts as an open switch. That is, there's no flow of current in the circuit when it's reverse biased, and when there's forward bias, it allows the flow of current through the circuit. And in a diode, this arrow mark represents the direction of current or the flow of current. So let's move on further. I need you guys to remember these parameters, which which I'm gonna explain in the further of the video. So VF is forward voltage drop, IR is reverse saturation current, or the current which flows in the circuit when reverse biased, and reverse breakdown voltage. So characteristics. So this let's just go through the PPT ones and let's explain later. So forward and reverse characteristics for low current silicon and germanium diodes is shown. From the silicon diode characteristics and figure, it is seen that the forward current IF remains very low, less than 100 microampere, until the diode forward bias voltage exceeds approximately 0.7 volt. You see the diagram over there. So let's try to understand. So the current flowing in the forward direction So let's say first the diode is in forward bias direction, which means that the positive terminal is connected to the positive and negative is connected to the negative. So the current flowing through the circuit in the forward bias is less than 100 microampere, as you can see. It's very less. But once the circuit reaches a voltage of 0.7, there is an extremely linear increase in current. A drastic change in the current. This is this point, 0.7 volt. This is referred to as the voltage drop or the forward voltage drop. When a diode reaches or when a circuit reaches the forward voltage drop, there's a linear increase in the current. At VF levels greater than 0.7 volt, IF increase almost linear, as we saw now. Because the diode reverse current IR is very much smaller than its forward current, the reverse characteristics are plotted with expanded current scales. Now, this is the reverse characteristics of the silicon diode. So this 0.7 volt is the voltage drop for silicon diode. As you can see, the reverse characteristics are on the left side, and it's on an extended scale because the current for reverse characteristics is on a reverse bias is very low, 100 nanometer. So when the voltage reaches minus 75 volt, the circuit breaks down. Because when this circuit reaches 75 volts, there is an extremely increase in the flow of current, which overheats the device, and the diode destroys or the circuit destroys. This the point where there is an extremely increase in current and reverse flow is known as reverse breakdown voltage. And for a silicon diode, the reverse breakdown voltage is minus 75. Similarly, we can see the forward and reverse characteristics for a germanium diode. It's just similar to silicon diode, where there is a very small flow of current in the forward characteristics until it reaches a forward voltage drop of 0.3, and you can see there is a huge increase in the forward current at 0.3. This 0.3 is termed as the forward voltage drop of germanium diode. And similarly, the reverse characteristics, the flow of current in reverse is not as small as the silicon diode of germanium. The germanium has a bit large reverse current than silicon. But still, when there's a volt of 50 volts in the reverse direction, the circuit, there's a huge amount of circuit flowing and huge amount of current flowing in the reverse direction. And this leads to the breakdown of the circuit due to overheating. So these are the characteristics of a diode. Now, let us see what an ideal diode is. An ideal diode is basically a diode which is impractical, but an ideal diode is referred to a diode which has zero forward resistance and zero forward voltage drop. So let us try to understand how the characteristics of an ideal diode will be. So there would be zero flow of current in reverse direction due to infinitely high resistance in the reverse direction. And we'll try to see if silicon and germanium diodes were ideal, how would their characteristics be? So yeah, so this is 0.3 volts and this is 0.7 volts. for an ideal, since it has zero forward resistance and zero forward voltage drop, the moment voltage increases to 0.3, there's a linear increase in forward current, and this is for the germanium diode. Because since 0.3 volt is the forward voltage drop of germanium diodes, and this is for silicon diodes, 0.7. Similarly, when the forward voltage increases to 0.7, there is a linear increase, extremely linear increase in the forward current of the silicon diode. So these are the characteristics and the introduction of diode. So we'll continue in the further videos.